U Centru za fotoniku Instituta za fiziku u Beogradu ubrzano se razvija jedna nova naučna oblast koja se naziva kvantna biofotonika. Ona se razvija kroz saradnju sa dve eminentne evropske istraživačke institucije, Univerzitet Fridrih Šiler Univerzitet kao i Italijanski Nacionalni istraživački savet. Ove dve institucije, zajedno sa Institutom za fiziku i Biološkim fakultetom Univerziteta u Beogradu, zajedno sarađuju na jednom twinning projektu koji se naziva BioQantSense. Kakve su potencijalne primene ovog projekta? Razgovarali smo sa doktorom Frančeskom Ribolijem iz Italijanskog Nacionalnog istraživačkog saveta.
My research activity is about photonics and different aspects of photonics for telecommunication and also for the point of view of fundamental physics. So from waveguides to photonic crystals. And also in the last year, my research activity focused on disordered photonics. In the lab that I have in Florence, we have a team that is studying the physics of disordered photonic systems and possible application with this kind of system. In this last year, the main activity is about cryptography and use the disordered photonic systems as a cryptographic primitive for application like anti-counterfeiting or authentications. The name of this kind of system, they name physical unclonable functions that are real physical systems that can be interrogated with a stimuli like a laser light, and after the stimuli it is possible to collect the response of the system and translate the response to a standard key that can be used for authentication processes. Physical unclonable functions are, as I said, cryptographic primitives that belong to the class of the so-called secret-free security. That means that you don't need any non-volatile memories to store your key inside your system because the key is the system itself. So it allows to, let's say, bypass the problem of storing keys inside devices. And another interesting feature of this kind of primitives are the fact that they are really unclonable because this kind of system are physical systems that, let's say, by definition, are not possible to clone to the microscopic levels. In our lab in Florence, we combine the expertise that we have in developing new photonic materials in order to enhance the complexity of this kind of systems. In particular, we use to realize the so-called photoresponsive materials that are systems that are able to, let's say, change their internal structure after a specific external stimuli. This allows to increase the internal complexity of the system itself and to increase the complexity to the generated key and again the resilience. There is again machine learning attack. We are a partner of this project. And the idea is to combine our expertise in disordered photonics and also our expertise to realize smart photonic materials with the expertise they have with imaging, in particular holographic imaging and quantum imaging. This allows, let's say, to understand if it is possible to use our paths, our physical unclonable function, in a more sophisticated protocols for authentication and anti-counterfeiting. The idea is to, let's say, to develop new materials and use these materials and characterize the materials in these labs in order to see if with this new kind of imaging techniques it is possible to add some value and increase the security of the cryptographic protocols.